Gemini Embedding 2, a native multimodal embedding model from Gemini. Google DeepMind has released a native multimodal embedding model that natively maps text, images, video, and crucially raw audio into a unified, continuous semantic space of up to 30n72 dimensions. It achieves state-of-the-art performance across the board. We're talking 62.9, recall at 1 on MSCOCO, 69.9 on the multilingual MTEB, and 84.0 on MTP code. The most massive breakthrough here is that it completely bypasses the need for ASR pipelines in audio retrieval, relying entirely on deep, bidirectional cross-modal fusion.
Yeah, it's a completely different paradigm for retrieval.
Welcome to AI Paper Slop, the YouTube series where we summarize the latest AI and tech papers for ML engineers and researchers. Our mission today is to understand exactly how Gemini Embedding 2 achieves this unified latent space without, suffering from the catastrophic forgetting or modality bias that plagues other multimodal models.
Right, because to understand how it achieves those wild benchmarks, we first have to look at the architectural shift from previous paradigms.
Okay, let's unpack this. What exactly is the shift?
Well, think about legacy late fusion models, things like CLEP, ALIGN, or even CICLIP2. They rely on modality-specific encoders and paired cross-modal data. So you have a separate encoder for vision, separate one for text, and so on.
Right, which, if you've ever built a production system, is basically a fragile, duct-taped nightmare to maintain.
Exactly. It's highly inefficient.
It's like a UN assembly where everyone needs a translator. You have all these intermediate text conversions just to make the data talk to each other. But Gemini Embedding 2 is like a single entity that just naturally thinks and dreams in every language, image, and sound at once.
That's a great way to put it. It relies on deep fusion. So instead of parallel tracks, it starts completely initialized from Gemini's foundation. It leverages those existing parameters as a massive pre-training stage.
Oh, wow. So it just uses the LLM's brain out of the box.
Pretty much. The raw formats, so the raw audio, the image patches, the video frames, they're converted into tokens natively supported by Gemini. There is no dedicated visual transformer acting as a middleman here.
Wait, really? None at all?
None. Once everything is tokenized, it's processed by a bidirectional transformer, and then they do a simple mean pooling along the sequence axis, followed by a linear projection to scale the embedding to the target dimension.
Okay, hold on. I need to push back on that a bit. If you initialize from a generative model like Gemini, you're dealing with a causal, autoregressive architecture. It's unidirectional by design, right?
Right. Usually it masks future tokens to predict the next one.
So how on earth do they generate dense, context-aware embeddings without that directional limitation causing massive modality bias?
Yeah, that is the core engineering hurdle. Generative models are causal, but embeddings need a holistic view. So they explicitly unmask the upper triangle of the attention matrix.
Meaning they adapt the causal backbone into a fully bidirectional one?
Exactly. By changing the attention mask to let every token attend to all other tokens, past and future simultaneously, they force the model to reason across the entire sequence. That prevents modality bias entirely.
So because the architecture natively accepts everything into this bidirectional blender, the next logical question is, how do you optimize the loss function?
Yeah, training this is incredibly delicate.
Because you have so many conflicting data types. How do they not degrade the baseline text performance?
Well, they use a multi-stage training recipe with noise contrastive estimation, or NCE loss, using in-batch negatives. But the real secret sauce here is Matryoshka Representation Learning, or MRL.
MRL. Okay, like the Russian nesting doll.
Exactly like that. Yeah. MRL allows a single model to support multiple embedding dimensions at the same time. The forward pass calculates the loss across nested subdimensions, specifically optimized for 768, 1536, and the maximum 3072.
That is massive for enterprise deployment. You don't have to train separate models for different storage budgets. You just truncate the vector.
Exactly. It's a huge efficiency gain. But the training itself is split into two phases. The first is pre-fine-tuning, or PFT.
And what does PFT entail?
They hit the model with enormous batches of noisy query target pairs across text, image, and code. The goal is to violently shift the model from autoregressive generation to encoding.
Right. Forcefully rewiring it to be an encoder.
Yeah. Then comes the fine-tuning stage, or FT. This is where they bring in audio, video, and documents. It requires really careful sampling rates across multitask batches with hard negatives.
Which brings up a common ML engineering headache. If you fine-tune heavily on, say, in-domain video data like MSR-VTT, won't it cause out-of-domain tasks like UCOOC2 to completely degrade?
Oh, it absolutely will. The paper explicitly shows that when they added MSR-VTT, performance there spiked. but out of domain UCOOC2 performance dropped.
So how do you fix one thing without breaking three others?
They use something called model soups.
Model soups?
Yeah. By systematically averaging weights from different fine-tuning checkpoints, they retain the baseline's robustness while capturing task-specific gains. For instance, interpolating a 2-to-1 ratio of the base model to the fine-tuned model.
Oh, that's incredibly smart. You just blend the parameter tensors to smooth out the degradation.
Exactly. But the true power of this multi-stage training in unified space is most clearly demonstrated in how the model handles audio.
Here's where it gets really interesting, because this completely breaks the traditional ASR bottleneck.
What's fascinating here is that the standard industry approach to audio search relies entirely on ASR. You have to extract a transcript to embed anything.
Which forces a rigid textual decision. Let's look at the massive sound embedding benchmark, or MSAB results. The classic acoustic ambiguity problem, right? Did the speaker say recognize speech or recognize speech?
Exactly. The ASR pipeline inherently suffers from error propagation. If the ASR guesses recognize speech, the retrieval system receives a fundamentally broken query. The intent is just gone.
But Gemini Embedding 2 processes native raw audio. It never touches a transcript.
Right. Native audio embedding preserves the ambiguity, the prosody, the pitch, and the intonation of the raw acoustic signal. It doesn't flatten sarcasm into a literal statement.
And the hard numbers back this up. Native audio achieves an MRR at 10 of 73.99, which straight up beats the ASR baseline of 70.40.
And we have to explicitly point out the massive cross-lingual generalization here, the passage cross-lang split in the benchmark.
Right, where you query in spoken French and retrieve a document in English.
Exactly. Native audio drives a 5.01 point enhancement there, because it isn't bounded by the phonetic rules or vocabulary limits of an intermediate transcriber.
So it handles raw audio beautifully. But does this generalized representation hold up when deployed into highly specialized, messy enterprise workflows like agentic RAG and dense code retrieval?
If we connect this to the bigger picture, it absolutely does. The zero-shot robustness across specialized data sets is incredible. They evaluated Astrolava for astronomy, MicroVQA for microscopy, and Recipe 1M for culinary arts.
Those are incredibly niche domains.
They are, and it scores 90.2 on Recipe 1M ingredients and 79.3 on MicroVQA.
That's huge because baselines like TIP-PS or SIGLIP2 are so spiky. I mean, TIP-PS is great at fine art on ArtCap, but it will absolutely bomb on biology imagery.
Right, but Gemini Embedding 2 is incredibly consistent. It eliminates those sharp peaks and valleys. And for document and code retrieval, the Fedora V2 document retrieval score is 64.9.
Which is notoriously hard because that requires understanding complex page layouts and embedded tables, not just OCR text.
Exactly. It deeply fuses visual and textual reasoning.
We also have to bring up the dramatic impact of synthetic data here. Using the generative Gemini model to create high-quality synthetic training data resulted in an average 15.8-point jump on challenging MTP Code V1 tasks.
Right, on things like Code Feedback MT and Synthetic Text 2 SQL.
So they basically use the frontier model as a teacher to map out complex logic that doesn't exist in scraped data. So what does this all mean for the ML engineers listening?
It means we are moving past the era of duct-taped pipelines. Gemini Embedding 2 isn't just an incremental update.
Right. By moving to a deep fusion bidirectional architecture initialized from an LLM and utilizing MRL and model soups, it offers a single out-of-the-box representation for RAG and search across all modalities.
Raw video, audio, text, code, everything in one continuous space.
It's a massive reduction in architectural overhead. But before we sign off, here's a final provocative thought for you to mull over. We've talked about how this model can natively encode the ambiguous acoustic features of a human voice, preserving tone, hesitation, and prosody without collapsing it into cold text.
Yeah, keeping the full emotional weight of the audio.
Exactly. So how will this change the future of semantic search? Will we soon be querying our personal archives not by the exact words someone used, but by the emotional vibe or the subtle hesitation in their voice when they said it? When the algorithm actually understands human intent directly from the sound wave, the concept of a search query changes forever.
It really does. It's a whole new frontier.
Thanks for joining us for this dive into the slop. We'll see you next time on AI Paper Slop.